A key requirement of many embedded and especially real-time systems is predictable performance. The time it takes to insert, update, or delete a row, record, or object in the database shouldn't vary wildly from one execution to the next. Likewise, the time to process the exact same query should be consistent over time. To the maximum extent possible, these metrics should be constant, irrespective of network traffic, server load, and other variables. So we'll talk about how predictability can be assured through the features of eXtremeDB HA. But predictability on its own is no good if it just means predictably inadequate. So we also want good or even excellent performance for all of our operations. So we'll look at the design choices for high availability and how those choices impact performance. When we're talking in the context of high availability, the need for reliability should be self-evident. After all, the goal of high availability is for the outside world to experience the system as a reliable one. In other words, it's there when we want it or when we need it. So, high availability involves redundant systems with a backup system to continue to make the system available if the primary system fails. But the embedded database or the HA subsystem should not be the cause of the failure that triggered the failover to a standby system. So we'll also look at some factors of eXtremeDB that contribute to its reliability, and as a corollary, how the absence of similar features could cast doubt on the reliability of alternatives. In the next few slides, we'll cover the basic concepts of high availability and explain some of the terminology that's frequently used. Like most technologies, it has its own vocabulary, and you need to be familiar with that vocabulary to sort through the information that's available from just about any resource. First, database systems have a concept called the ACID properties of transactions. Supporting transactions with the ACID properties is a litmus test of sorts for any database management system. If a database management system doesn't support the ACID properties, then it's really not a database management system at all. It's more like a record manager. Now, I need to soften that up a little bit because in the last couple of years, there have been a whole bevy of products released under the umbrella of NoSQL. And these NoSQL databases may offer transactions that support the ACID properties, but more often they support a concept called eventual consistency. But that whole discussion could be an entire webinar topic on its own, so I'm just going to leave it at that for now. At any rate, ACID is an acronym for atomicity, consistency, isolation, and durability. So let me explain each one of those. Atomicity is defining a unit of work, a group of changes to the database that all need to succeed or fail together. So they're an atomic operation. Consistency has a couple of meanings. First of all, when we apply a transaction to the database, we're moving that database from one consistent state to another consistent state. And secondly, that every process or every task that's working with the database has a consistent view of the database. That's closely related to the next property, isolation, which means that any changes that are being made by one transaction cannot be seen by any other transaction until the first transaction is committed to the database. In other words, those changes made in the scope of that transaction are isolated to that transaction until that transaction commits its work. And then finally, the D in ACID is for durability, which simply means that once a transaction is successfully committed, it's durable, it's permanent. You always have to take durability in the proper context, though. It's durable as long as the database itself is durable. Now, for an on-disk database, that means that the media is durable. If you have a head crash and you lose your hard disk, your transaction isn't very durable anymore. Same thing really applies to in-memory databases. The database and the transactions are durable as long as the database itself is, but when you turn off your computer, whatever's in memory goes away. In either case, whether it's in memory or on disk, if you're really concerned about durability, you better have a backup. Now, database replication is the process of duplicating or producing a copy of a database. High availability databases achieve high availability through database replication. The implementation of replication can be based upon replicating transactions or replicating individual database objects, which could be columns, rows, or database pages, for instance. Arguably, transaction replication is the best because it has the ability to preserve the logical consistency of the database, just like the ACID properties do. But replication can be done at several levels. For example, there could be the equivalent of a trigger that pushes insert, updates, and deletes of rows of a table out to the replicas. Or a replication can push entire database pages. In addition, replication can be real-time, or it can be transaction log-based, wherein a separate process picks up data as it's appended to a log file and then transmits that information to the replicas. One of the goals of high availability is to replicate not just the database contents, but also the state of the system. There are often several processes that constitute a single system, and not all of those processes are necessarily directly associated with the database. But those, what I call unassociated processes or systems, may still have dependencies on the database. For example, a protocol stack might need to know that some quality of service parameter has changed. Normally that would occur through database event notifications or triggers. Ideally, when the database changes are replicated to a standby copy, the replication will trigger the same events in the same order so that the standby can mirror the state of the master system accurately and completely. If the database high availability subsystem doesn't do this, then you have more work to do yourself at the application level to effectively replicate the entire state of the system. In addition to the different mechanics for replication that I discussed on the previous slide, there are different categorizations of high availability systems. These are eager, synchronous, or two-safe, lazy, asynchronous, and one-safe, and for two-safe, with eXtremeDB in particular, there's a time-cognizant two-phase commit protocol. So we'll look at each of those. Two-safe is so named because there's considered to be two completely synchronized copies of the database at all points in time. This is accomplished by effecting the replication in a synchronous manner. In other words, the master application, when it commits a transaction to the database, is blocked until that transaction is replicated to the standby copy, or copies if there's more than one, and only then is control returned to the master application, which can then continue processing. It's also called eager replication. This approach eliminates conflicts because the master and the standby copies are updated in lockstep. So it's a potentially less complex solution. Therefore, there's less code involved, which means it has a smaller code footprint, and less complexity, which also generally means it's less prone to defects. It also has the advantage of ensuring that every copy of the database is identical at all points in time. So a query issued against any copy of the database will yield the same result set as if it was issued against any other copy of the database. Assuming that the database system allows replicas to be read by local processes, and eXtremeDB does, this means that a query executed anywhere is going to have the same result set as if it was issued against the master database, so our queries can be distributed or spread throughout the system for load balancing. On the negative side of the ledger, the synchronous nature of the two-safe model means that the throughput is not exceptionally high. Remember what I just said, the master is blocked while the replicas are applying the transaction to their databases. With eXtremeDB, we do get some parallelism. The master database runtime is going to be updating its indexes while it's waiting for the replicas to reply. The eXtremeDB high availability implements two-safe replication through a time-cognizant two-phase commit protocol. First of all, it's a two-phase commit protocol. So the first phase of the commit is started on the master, and then the master sends the transaction data to the replicas and waits for the replicas to reply. The replicas do the other phase of the commit, apply the transaction to their local database copies, and then send the return code to the master. The master compares its own return code to that of the replicas and then completes the transaction. Because the transactions are synchronous and the databases are identical at all points in time, if a transaction succeeded on the master, then it also has to succeed on the replica. Remember, the databases are identical, so if it succeeded on the master, it's got to succeed on the replica. If it didn't, then there's just something fundamentally wrong with the replica, and it's going to be decommissioned. It'll be disconnected from the master, and that replica will have to reconnect and get resynchronized with the master. And then the time cognizance part of that time cognizant two-phase commit protocol is the manner in which eXtremeDB gains back predictability in the context of unpredictable network latency. So every communication between the master and the replica has a time threshold associated with it. And if that threshold is exceeded, then we return control back to either the master or the replica, as the case may be. So there's 4 types of communications. There's the initial synchronization, which happens when a replica attaches to a master. The master has to send its database through the communication channel to the replica. And the time that it takes to send that copy of the database through the channel has a threshold associated with it. And if it takes longer than that amount of time, then we'll just give up and we'll return control back to the master application. Once we have the initial synchronization completed, every transaction that's applied to the master has to be sent over to the replica. So the amount of time that it takes to send a transaction through the communication channel to the replica also has a time threshold associated with it. And if we can't get it done within that period of time, once again, we give up. The assumption being that there's either something wrong with the communication channel or there's something wrong with the replica. And once again, we're going to disconnect the replica and it will have to reconnect later and get resynchronized. Once a replica has the transaction data, then it has a prescribed amount of time to apply that transaction and send its result code back to the master. And then finally, there's the equivalent of a heartbeat. The replica is going to expect to receive a transaction from the master every n seconds or microseconds or milliseconds or whatever your threshold is. And if it doesn't receive a transaction from the master within that period of time, it's going to assume that the master isn't there anymore and will trigger the failover process. The other possibility is one-safe replication. One-safe, as its name implies, has lower consistency, but will exhibit better and perhaps much better performance due to its asynchronous nature. In this case, the master isn't blocked while the replicas apply the transaction to their local copies. In this case, the master is going to put the transaction data into the communication channel and then immediately return control to the master application, so it's not blocked. In general, because the master doesn't wait, the one-safe model can introduce the possibility of conflicts that then have to be resolved through some reconciliation process. That would naturally complicate the implementation. In the specific case of eXtremeDB, there is no possibility of conflicts even with the one-safe model. And while database systems may allow replicas to be queried in the one-safe model, and again eXtremeDB does, you lose that guarantee that a query is going to return the same result set regardless of which copy of the database it's issued against. There may be some time lag between when the transaction gets applied to the master, put into the transaction, or into the communication channel rather, and then gets applied to one or more of the replicas. So because of that time lag, you lose that guarantee that a query issued against any one copy of the database will return exactly the same result set if it was issued against any other copy of the database. In many cases, that simply doesn't matter. So one-safe is actually a very popular approach because of the much better performance that it delivers compared to two-safe.